Thank you. I'm Abe Clements. This work was done in conjunction with some of my collaborators, Naif, Khaled, Prashast, Jinkyu, Sarab Bagchi, and Matthias Pear. Sarab Bagchi and Matthias Pear are my co-advisors, and I'm a second-year PhD student at Purdue University. I'll be discussing protecting bare metal embedded systems with privilege overlays. So first off, what is a bare metal system? A bare metal system is a system without an operating system. It runs directly on the hardware. There is no separation between, well, there is no kernel or operating system. If there's an operating system, it provides lightweight threading and is compiled with the application. There is no separation between user space or kernel space. It's all one memory space. These systems have very tight constraints on memory and runtime and energy. A large system would have like a megabyte of memory for code and 120 kilobytes of RAM. This would be a kind of a larger end bare metal system. Some examples of these systems are Amazon's Dash button, smart door locks, engine controllers, SD card controllers. So inside of your SD card, there's a microcontroller that handles flashware leveling. This is an example. Those run bare metal code. Wi-Fi system on a chips. These are in your cell phone. They run the Wi-Fi connections. Because of the constraints, the small memory sizes, the low power requirements, security is often just left out. As an example, Google's Project Zero earlier this month disclosed that they'd found vulnerabilities in Broadcom's Wi-Fi system on a chip that enabled them to, just by having Wi-Fi on your phone on, take control of your application processor. They were first able to take control of the Wi-Fi system on a chip and then use that to elevate and obtain accesses within the kernel on the application processor. So security on these systems is important, and it's just been left out. So let's look a little more closely at these embedded systems. This is a memory layout. So an important thing to know about their layout is it's fixed. Everything is physical memory. Down at the bottom, you've got flash. This is where your code would be located, and your code will be at a fixed address. If everybody's using the same micro, that's where your code is. The RAM, same thing, fixed address, and it will be usually in the middle. As you go up, you have peripherals that are mapped into your memory. I'll often refer to these as memory mapped registers. If you want to control one of these things, you read or write the fixed address of the I/O. And they also contain some security hardware. But we'll find that everything on the system runs with a single execution domain. Everything runs as root. If there is security hardware, it's unused or trivially bypassed. As an example, because everything's in root and the security hardware is configured by writing to the fixed memory locations where it's located, a single memory corruption vulnerability would allow you to just turn off any sort of security hardware that's enabled. Any sensitive I/O would be always accessible. Your RAM, any of your global data or stack is vulnerable to stack smashing, code injection, global data corruption. And your code and your stack employ no ROP defenses. Essentially, we're sitting 30 years back on these devices from desktops today. So we have defenses for all of these on desktops. Why don't we have them on these systems? One of the chief challenges to this is there's a single application. There's no separation of privileges. All of these defenses we have on your desktop rely on usually your operating system to configure the permissions for your memory pages. We don't have an operating system to configure the permissions. If you can configure them just in the one if you configure them in your application can just disable them. The systems lack a memory management unit. They have no virtual memory. This limits all of your defenses to physical memory. And so you have a small space. So ALSR doesn't work because you have a very small memory space. Again, the small memory sizes limit diversification. They also mean that any defense that you apply must have very small memory overhead. And the same thing with runtime constraints. Combined, these have led to security just being left off these systems. To address this, we've developed Epoxy, which is an acronym for Embedded Privilege Overlay Across X Hardware for Y Software. It's an LLVM compiler, and we targeted for our proof of concepts the Cortex-M series of microcontrollers. It protects against code injection, control flow hijacking, data corruption, direct manipulation of I/O. And chief to its protections is this privilege overlays. This creates two privilege levels, a privileged and an unprivileged level, using some static analysis. And this is foundation to us of enabling other defenses to be applied. So I'll go through each of these protections and how they're applied throughout the remainder of this presentation. First, though, our threat model. We're assuming an arbitrary memory corruption. There's an attacker with an arbitrary memory corruption. The attacker either wants to obtain execution or corrupt specific global data. He does not have physical access to the device under attack. We require that the hardware supports 2 privilege level execution modes. So privileged and unprivileged execution modes. We need a memory protection unit. This is a piece of hardware that's in modern microcontrollers that enables setting read, write, execute permissions on physical memory. And then we also require that the memory usage be determined a priori. So the maximum memory that the application will use has to be able to be determined a priori, which is a restriction on these systems that already exists. You have such small memory space, you have to know that it's going to be able to execute within the memory that you have. So as I go through this presentation, I'll take the application that we show here, and I'll build up the defenses around it. So here I'm showing, again, that application's memory space with everything's privileged, right? And everything's accessible. So as we go through the defenses, I'll change colors and add to the defenses and show how they work. So the first approach that we perform is called privilege overlay. This creates the multiple privilege layers. It enables the developer to assume access to all memory locations. So as the developer is developing an application for these systems, they have this application has to manage all the hardware. It needs to be able to access it. But for security requirements, we need to restrict access to some of this so that it's not trivially bypassed. For example, the memory protection unit. If the developer enables it, but we leave everything as privileged, then it's easily turned off. However, this one application has to be able to enable the memory protection unit. So the way we do this is we let the developer assume access to everything. We then use static analysis to identify any privileged operation. So privileged operations are instructions that are defined by the architecture that have to have privileges to execute. An example would be enabling and disabling interrupts. And then we also identify access to any of these peripherals that require privileges. For example, the memory protection configuration unit or developer-defined sensitive I/O. So these, again, are fixed memory locations where you read and write to access these peripherals. So our static analysis identifies these reads and writes and automatically elevates privileges. To do this, we inject several different pieces of code with epoxy. So we configure the memory protection unit. This is code that's injected automatically by the compiler. It enforces DEP, or data execution prevention, and restricts access to these sensitive peripherals or sensitive registers. We reduce the execution privileges of the entire application. We just kick the whole application out of privilege mode, and then we insert requests around restricted operations, and then we elevate those. We have a handler, we inject a handler to handle those requests. So I'll go through an example to show how this happens. So in this example, the orange denotes privileged execution, and we've got a UART that is located at the address deadbeef, and we're reading from that UART. This is a sensitive operation. So when we apply privileged operations, the first thing we'll do is we'll kick the application out of privilege mode. So blue denotes unprivileged execution. Then we will, the static analysis will identify that this read to this fixed address is sensitive. So we'll insert a request for privileges just preceding it, and we'll drop privileges immediately after, which results in just a small orange section with privileges executing. So as you can see, we reduced drastically the amount of operations that require privileges and enable this operation and just this operation to occur with privileges. So after applying privilege overlaying, if we tie this back to desktops, we have enabled DEP. We have data execution prevention. This means that our RAM, our global data, and our stack are set to read, write, no execute. You can't execute them. Code injection has been stopped. In our code is set to read, execute. It's no longer writable, and this provides our code integrity. And there are some small areas which require privileges, but the rest of it's unprivileged execution. And finally, any sensitive I/O is also restricted to privileged execution. To further protect the system, we apply defenses against ROP attack. We use SafeStack and diversification. SafeStack is from the Code Pointer Integrity project from OSDI in 2014. it protects against stack smashing. The way it works is it does static analysis on the program, identifies any variables that are unsafe, and moves them to a separate unsafe stack. And an unsafe variable is a variable that either its address escapes the bounds of the current function, or it's used in pointer arithmetic in a way that we can't prove is safe. And then only those functions which use variables that are unsafe actually use the unsafe stack frame. So the problem is that it relied on virtual memory. We don't have that. So we have adapted it to this bare metal systems. The way we've done that, safe stack's a split stack approach. So it splits it into two parts. We move the unsafe stack to the top of memory, change its direction so that it's growing away from global data. We use the MPU to configure a guard region which is inaccessible to both privileged and unprivileged execution. So in this way, we have a separate region for the unsafe stack, and we have a separate region for the stack. We've isolated all the unsafe globals up into the unsafe stack region. And then to further protect them, we apply some diversification. So the way that we apply diversification is epoxy takes a seed. Based off that seed, it generates a unique binary. When we look inside this binary, we have the RAM, and at the green area, we've got unused memory. We take that unused memory, we break it up into 5 chunks of padding. These 5 chunks of padding we distribute throughout the remainder of the application. A portion goes to providing randomization to the stack address. Part of it's combined with the data, the BSS, and then between the heap and the unsafe stack. When we look in the data section, there's a number of global variables. In this example, we've got A, B, C, D. Those are randomized along with that padding to help increase the entropy that we can create with this. The BSS is randomized in a similar manner. That diversifies the RAM. To diversify the code, we have functions foo, bar, baz, bar2, and foo. First thing we do is we inject a handler. This will handle any inappropriate execution. We then fill the rest of memory with jumps to this handler, essentially single byte instruction or 4-byte instructions which jump to the handler. We randomize the location of everything, which enables this randomizes all the locations of all the ROP gadgets in the code. And if execution ever goes to a place which isn't expected to execute, it will go to this handler, enabling it to be detected. So after applying all of these defenses, we have isolated unsafe locals to their own separate stack. The global data is protected. Stack smashing has been prevented on the stack by safe stack. We have ROP protections from diversity and ROP. But it's essential with all of these protections enabled, we now have protections against ROP, code injection, access to specific global variables, and access to sensitive I/O. It's important, though, for these systems that they have small overhead and performance. So to evaluate this, we evaluated the BEEBS benchmarks, which is a suite of 76 different applications that are adapted to measure performance on bare metal applications. We evaluated 75 of these. One of them allocated more memory than my system has. So then in these tables, we've got runtime on top, power on the bottom. SS is safe stack only, so we value binaries with only safe stack applied. The second one's privilege overlay, the center column, which has, we've only applied privilege overlay, and then all of the defenses on the far right column. From it, you can see that we average around 1% for overhead, and our power is about 2.2%. We also tested 3 IoT applications. These applications, as you can see, that they always use under 10% of energy or runtime, and that the energy and runtime are highly correlated, with the exception of the pin lock of the first one, that it's blocking on I/O, it's reading from a serial port, and because of that, the execution time gets hidden, but the energy distribution does not get hidden. We have very limited ability to make entropy on these systems. We have very limited memory, so we wanted to understand how ROP attacks would work on these systems. So to do this, we compiled 1,000 variants of each of these applications, and then we looked at how many gadgets existed across a given number of variants. So in the center, we've got, the 2 column represents the 2 gadgets survived, and then last represents the number at which the last gadget survived across 2 variants. And so for the worst case, we have around 107, so around 10%. The 10% of the or 10% of the variants would be able to be attacked by one gadget. And since gadgets or ROP attacks usually require multiple gadgets, the ability to create a ROP attack that scales across a large set of devices would be greatly hindered by the application of epoxy. Then we want to compare how many privileged instructions we execute. To do this, we took FreeRTOS, which is a very common operating system used for bare metal systems. It has a secure version that's very infrequently used that uses the memory protection unit to apply some code and data execution prevention. However, by its default configuration, it doesn't even do that. So we ported the applications to FreeRTOS MPU, and you find that we use well under 1% of instructions are privileged, and the FreeRTOS MPU around 95% require privileges. This is because FreeRTOS requires that if any instruction uses privileges, the entire thread also requires privileges. In conclusion, we fast forward bare metal security 3 decades by recompiling the application. We provide state-of-the-art protections which are comparable or exceed those currently deployed on desktops. We don't require rewriting the application, provide strong stack protections by an adapted safe stack, minimize the number of privileged instructions executed, and diversify all memory. We also meet the runtime requirements for bare metal systems and memory and energy. We've also open sourced our compiler. It's available at the following location. Any questions?
Questions?
Hi, Pim Vullos, NXP Semiconductors. So I was interested in the performance figures that you showed, where actually using epoxy gave improvement, or how should I see these figures, and can you explain why?
Okay, so it's a diversifying compiler, so the instructions change from each binary. And so the way we get an improvement or a speed up is sometimes by randomizing the locations of functions, it enables the compiler to identify additional optimizations. The other things that occurs is sometimes you have long jumps and short jumps, essentially, and which require a different number of instructions. So by randomizing the binary, we obtain a different mixture of basically immediate addressing versus absolute addressing.
Okay, thank you.
So I also have a quick question. When you are identifying sensitive operations, do you need users to annotate the code to tell you where sensitive data is?
So in our, currently all of the sensitive operations are accesses to peripherals, which have fixed addresses that are set in the hardware. So for those that are specific to, like, that are common across an architecture, say ARM Cortex M4s, the system control blocks have the same address on all of those. Those ones our compiler handles automatically. If I, as a developer, say, in this context, this serial port is sensitive, I want it to be sensitive, then you can provide that to the compiler and it will include it in its analysis.
You didn't do that in your experiments, I suppose, right?
The pin lock actually applies the UART in the pin lock is sensitive, is defined as sensitive.
Okay, thank you. Any other questions? Okay, let's thank the speaker again.